Greetings. There has been quite a lot of chat on the internet and through YouTube about the Mandela Effect and what could possibly be causing it. So in this video, I'm going to argue that the Mandela Effect cannot be caused by quantum computing, which is one of the theories or one of the propositions that have been put forward by quite a lot of people. And I'm going to show why this cannot be the case, why this cannot be the case. Quantum computing, the reason why people think that quantum computing is behind the Mandela Effect is basically because of two weird quantum physics things. The first one is superposition, and the second one is entanglement. These two things are these are discoveries, or these are characteristics of subatomic particles that have been discovered in quantum physics research, and they are behind the operations of quantum computers. So, for example, while a conventional computer operates or does calculations just by moving electrons around or shifting electrons around, a quantum computer would perform calculations in a way that actually uses these two very interesting characteristics of subatomic particles, and they will use these characteristics in a very clever way to produce some outputs, to produce some calculations. And so this is the basic difference between conventional computers or conventional computing and quantum computing. Now we are going to go and have a quick chat about superposition, what it is. I don't think that we're going to explain this to a lot of people because these are relatively complex issues. So I really encourage you to study more about these two things, superposition and entanglement. So I'm just going to discuss this with a really very broad brush. So consider, for example, that you're holding a whip. So you're facing the screen right now, and you're holding a whip. There are a number of different ways where you can swing this whip. For example, there is an upside down. You could swing it in that way. So let's call that vibration mode. Let's call it 1. And there is another another possible way that you could swing this whip would be from side to side. So let's call that mode of vibration mode 0. Now, this is something that is very similar to what happens with a subatomic particle or a wave, and so this shows that this wave has different ways of vibrating, so different modes of vibration. Now, what has been discovered is that subatomic particles actually can be at both modes of vibration in any one time, or they can actually have multiple modes of vibration in any time. They don't have to quote unquote choose one mode of vibration in order to exist. So this is something that is very interesting. It's a fundamental tenet of quantum computing, or quantum physics. And the way that I found to kind of understand these superposition of states is by analogy. So consider, for example, that you have a sheet of paper, and you could draw a line on this sheet of paper separating the left from right. Now, you could have a pencil that is on the right side of the paper, and that the pencil will touch the paper to the right of the line, and it would leave a small dot, as you can see there. Another possibility is that you could touch the tip of the pencil to the left of the line, and this action would leave a dot, a small dot, to the left of the line. But then, so these two things, or these two states, take place when the tip of the pencil is actually touching the paper. So the paper is a two-dimensional structure, or a two-dimensional entity, and when the tip of the pencil touches the paper, the tip of the pencil is part of this two-dimensional structure. So you only have a two-dimensional system in this case. Now, what would happen, for example, if this situation arises? If you hold the tip of the pencil above the paper. So now what you're going to see is that you don't have a two-dimensional situation anymore. Now you have a three-dimension situation. Now the position of the tip of the pencil cannot be determined by a two-dimensional system of coordinates, because now there is one additional dimension. So the paper is hovering there maybe 1 or 2 centimeters above the piece of paper, and you can't really define the tip of the pencil using a two-dimensional set of coordinates. So what happens there in this shaded area that you can see, the shaded area represents all of the possible points where the tip of the pencil could touch the paper if I dropped it from this height. So this area is a zone of probability. So it's an area of probability, and if we draw the line on that, you will see that the shade, or the area of probability, is half to the left and half to the right. So in this case, the tip, you could even say that the tip of the pencil, the area of probability where the tip of the pencil could actually touch the paper, is both to the left and to the right of the line. So this is a state of superposition. But this state of superposition only exists because now the object, which is the tip of the pencil, is in another dimension. You don't have the two-dimensional system anymore. Now you have a three-dimensional system whereby this element, which is the tip of the pencil, is separated by your reference, your two-dimensional framework of reference, by one additional dimension. So it's like the tip of the pencil is something that exists in a parallel dimension, or even you could even say exists in a parallel universe, so to speak, because there is no way that a two-dimensional entity would be able to understand where the tip of the pencil is in this system, because the tip of the pencil is completely outside the two-dimensional universe represented by the piece of paper. So the concept of superposition, as I explained with this very crude example of a two-dimensional piece of paper and a pencil, the concept of superposition is consistent with the notion that the particle or a particle exists in a higher parallel dimension or parallel universe. It just hasn't been sucked down into our universe yet. So it exists in a state that is potential in our universe, but it's really very real in this parallel universe where the particle really resides. So what happens is the particle or the state of superposition of possible states is the case in our universe, at least until the particle or the real state of the particle is observed or measured. That is, when the particle is pulled down from this higher dimensional universe where it exists, and it's pulled down into the lower dimensional reality by the consciousness of the observer. So the particle comes down from wherever it is, and it's brought down to our physical universe by the act of conscious observation, or conscious measurement. And this, of course, can only be done by a conscious observer. So this is the role of consciousness in quantum physics, at least in my humble opinion. Now, entanglement is something that is relatively similar, or it has a similar dynamics. Now, if you consider, for example, electrons, I'm just depicting electrons or subatomic particles as these, wiggly rubber bands. For no particular reason, I'm not trying to evoke here an image of string theory, but I just found this quite interesting. So you have two subatomic particles, and let's say you shift one subatomic particle to the left, and you shift the other subatomic particle to the right, just so they are separated by a physical distance. Now, any communication between these two subatomic particles will have to take place in our known universe, in our physical, three-dimensional, or four-dimensional, if you consider time, universe. The problem is that there is a limitation to how quickly this communication can take place. And the limitation is, of course, the speed of light. So nothing can go from the particle on the left to the particle on the right at a speed higher than the speed of light, at least in our conventional understanding of physics. The funny thing is that quantum physics has shown that this is not how things work. So let's say you have two subatomic particles, and they are vibrating in whatever state. So they are, I'm just using these, the squiggly rubber bands, not as an evocation of string theory, but I'm just using this as a graphical device to show when things, or when subatomic particles are out of synchronicity, or they are acting in a synchronous way. So you think of these two subatomic particles, you do the same experiment that we had before. You have the two subatomic particles existing in this four-dimensional space-time continuum that we have. You hold these two subatomic particles that are now vibrating in synchronicity, and you separate them by a physical distance. And what you notice is that the subatomic particles, they are entangled, they have been entangled, and they are a number of ways to entangle subatomic particles, but what you notice is what happens to one particle is immediately and instantaneously felt by the other particle. So if the wave function of the particle on the left collapses, the wave function on the particle of the right will also collapse. If the particle on the left assumes a certain position from a previous state of superposition, the particle on the right will also have an instantaneous movement, an instantaneous reaction to that. And what experiments have already established is that this communication, quote unquote, happens instantaneously. So even if the distance between the two particles is finite, or even if the distance is really very, very large, the communication is instantaneous. So how can you have instantaneous communication? Well, the only way for you to have this instantaneous communication over a finite and non-zero physical distance is if you have infinite velocity. Now, infinite velocity or infinite speed is, of course, ruled out by relativity, because relativity says, the theory of relativity says that nothing can travel faster than the speed of light in our four-dimensional universe. Therefore, what happens is that the communication between these two particles has to be taking place outside the four-dimensional space-time continuum that we call our physical universe. Therefore, what you will conclude is that the concept of entanglement is also consistent with the notion that particle systems can operate, at least in part, outside our space-time, at least in part outside our universe. So as you can see, both concepts of superposition and entanglement, they are such that they require the notion of stuff happening outside our physical universe. And then this guy called David Deutsch, he's considered to be the father of quantum computing. He gave a speech using this analogy of parallel universes, which we have just discussed before, and he said this. He said, quantum computation will be the first technology that allows useful tasks to be performed in collaboration between parallel universes. So this is the interpretation of quantum physics, that when you have all of these weird things happening, such as entanglement and superposition, you're necessarily talking about parallel universes, because you're talking about stuff that cannot be defined within our four-dimensional grid of space-time. Now, then the conclusion is, or the conclusion for some people is that, look, if quantum computing is using things such as entanglement and superposition, and entanglement and superposition are messing up with parallel universes, then they are also messing up with parallel timelines. And therefore, they necessarily are connected to the Mandela Effect. This is how the whole link between the Mandela Effect and quantum computing arose. Now, the truth is that superposition is a natural characteristic of all subatomic particles. It happens all the time. It's something that happens all the time. For example, the light around you right now, as you're watching this video, the light around you consists of photons in superposition states. So superposition is not something that is happening only inside a quantum supercomputer. Superposition is something that happens every freaking time, every minute of our lives. Now, entanglement is also a natural characteristic of all subatomic particles. It happens all the time. Particles are entangled all the time. Now, there is something that is called a weak entanglement. And this is really very, very common. And there is something that is called a maximum entanglement, which is when particles are really intrinsically interconnected by this link that sits outside our four-dimensional universe. And they're very strongly interconnected. So I'll give you that. Maximum entanglement can only be achieved in lab conditions. Now, this is, or at least it appears to be something that has only arisen recently since we started messing up with quantum physics and subatomic particles. Now, the problem is that this maximum entanglement can only be achieved between two subatomic particles. Between two subatomic particles, a pair of subatomic particles. This is a principle called quantum monogamy. If you have something that is more, if you have a system that uses more than two subatomic particles, you cannot be talking about maximum entanglement. Therefore, the entanglement that takes place in a super quantum computer, such as D-Wave. D-Wave, apparently they use something like 512 qubits or 512 entangled particles or entangled nuclei. I'm not very sure what they use. It cannot be maximum entanglement. So it has to be this flavor of entanglement that is considered, that is called a weaker entanglement. And the thing is that this weak entanglement is really, really, really very common. Every atom in your body right now has electrons that are in a state of weak entanglement. So what you realize is that this idea that entanglement and superposition are only seen in quantum computing and lab conditions, and therefore they lead to the Mandela Effect. This is not true, because what happens is that pretty much superposition and weak entanglement is something that is absolutely ubiquitous. It's everywhere. It's everywhere, including inside your own body right now. Quantum computing has only found a way to make these two principles calculate stuff. So it's a very clever way to do this. It's something that has never been done before, but the principles themselves are manifest in every aspect of your life, including your own body. So you can't really say that these two things are messing up with timelines, messing up with parallel universes, and causing the Mandela Effect. So to conclude, I'm just going to use a slide that I had already used in another video, placing four very interesting and four very interesting aspects of the Mandela Effect. The first aspect is that the Mandela Effect is physical and real. It's not imagined. The second aspect is that the Mandela Effect is a benign effect. It's not benign to every person. There is a group out there that is really uncomfortable with the Mandela Effect, but for most of us, most of mankind, most of humankind, the Mandela Effect is something that is going to bring a very positive outcome. The other issue is that the Mandela Effect does not seem to be restricted to Earth. There are other consciences or consciousnesses, I don't know what the plural is, outside this planet that are also experiencing the Mandela Effect. And the Mandela Effect is something that has been caused by a shift in consciousness on this planet and outside of this planet as well. So thank you very much for watching. I hope that this was useful. Please share, like, and subscribe, and we'll be back with more later. Thank you. Bye.